Imagine a world where machines can truly see. They can look at a photograph or a live video feed. They can understand the content within these images. This is not a distant dream from a science fiction movie. It is a reality that is unfolding right now, all around us. Computers are rapidly learning to interpret the rich, complex world of visual information. This newfound ability is profoundly changing many aspects of our daily lives and industries. It represents a very exciting and significant development in the field of modern technology. We are teaching machines a form of perception, opening up countless new possibilities for the future. So what exactly is a neural network, this technology that seems almost like a thinking machine? In simple terms, you can think of it as a computational model inspired by our brains. A neural network is constructed from many interconnected processing units called nodes. These neurons are organized into layers, and information flows through them. They learn from large data sets, identifying complex patterns. This ability makes them powerful for tasks like image processing. Neural networks have revolutionized how we handle visual data. Image processing involves techniques to perform operations on digital pictures. Tasks include making images clearer, identifying objects, and recognizing faces. The goal is to extract meaningful information or enhance images. Neural networks learn visual features directly from image data. They adapt to diverse real-world images, transforming capabilities across domains. Join us as we explore this revolution in image understanding. At the heart of a neural network is the artificial neuron. Think of it as a tiny information processor. Inspired by biological neurons, it receives signals, performs calculations, and produces an output. Each neuron acts like a cog in a larger machine. These units build complex, intelligent behaviors. Weights determine the importance of each input. Through training, networks adjust these weights. This tuning enables tasks like object recognition. The final output is sent to other neurons. Organizing neurons for teamwork. Artificial neurons are organized into layers. Think of it like a company with different departments. Information flows from one layer to the next. Typically, there are 3 types of layers: input, hidden, and output. The input layer receives initial data. Hidden layers process the data. The output layer produces the final result. This structure is key to neural network functionality. Section 3. The training process. How networks learn from examples. Neural networks learn through a process called training. Think of it like teaching a child with examples. Show many pictures of cats to teach what a cat is. Similarly, networks learn from vast data. Labeled data guides the learning process. The network adjusts its settings to minimize errors. Over time, it becomes more accurate. Section 4. Learning perfected. Refining the network's knowledge. Once the network makes a prediction and the error is calculated, the next crucial step is to use this error information to improve the network. The network needs to learn from its mistakes. This is achieved by adjusting the weights of the connections between the neurons. The process for doing this efficiently is often known by a technical name, backpropagation. But the core idea is simple. The error calculated at the output layer is propagated backward through the network, layer by layer. As it travels back, it tells each weight how much it contributed to the overall error. Each weight is then adjusted slightly in a direction that should reduce that error in the future. These adjustments to the weights are not made drastically all at once. Instead, they are made in small, careful steps. A parameter called the learning rate controls the size of these adjustments. If the learning rate is too large, the network might make big changes that overshoot the optimal solution, and it might never settle on good weights. If the learning rate is too small, the training process can become incredibly slow, requiring a very long time to achieve good performance. Choosing an appropriate learning rate is an important part of designing and training a neural network effectively. It is a delicate balance between learning quickly and learning accurately. The entire cycle of feeding data forward, calculating the error, and adjusting weights backward is repeated many times. The network processes the entire set of training images multiple times. Each complete pass through all the training examples is called an epoch. A neural network might need to be trained for tens, hundreds, or even thousands of epochs before its performance becomes satisfactory. With each epoch, the network's weights are gradually refined. The overall error on the training data should decrease. This iterative refinement is like a sculptor slowly chipping away at a block of stone, gradually revealing the desired form. It takes patience and many small adjustments. The ultimate aim of training a neural network is not just for it to perform well on the data it has already seen during training. That would be like a student who only memorizes the answers to practice questions but cannot solve new problems. The true test of a well-trained network is its ability to generalize. This means it should be able to make accurate predictions on new, previously unseen data. If a network generalizes well, it means it has truly learned the underlying patterns and features from the training data, rather than just memorizing the examples. Achieving good generalization is the key to building useful and reliable neural network models for real-world applications like image processing. And seeing the world image classification with neural networks. Image classification assigns a single label to an image. Neural networks, especially CNNs, excel at this task. They learn features from images during training. Initial layers detect edges, deeper layers form complex patterns. Large, diverse datasets like ImageNet are crucial. Applications include sorting photos, categorizing products, and medical scans. Finding needles in haystacks. Object detection explained. Object detection identifies and locates objects in an image. It's more complex than image classification. It finds precise positions of objects. For example, it can locate a dog in an image. This helps understand spatial relationships. It provides richer image content understanding. Neural networks output class labels and bounding boxes. They identify objects like people and traffic lights, and provide bounding box coordinates. Bounding boxes frame detected items. Modern networks detect multiple objects in cluttered images. They distinguish overlapping objects. The output is more structured than classification. It lists detected objects, including class, confidence score, and coordinates. This allows sophisticated visual interactions. For example, tracking object movement over time. It's powerful for real-world applications, indispensable in many technologies. Self-driving cars use it to perceive surroundings, identifying pedestrians, vehicles, and signals. Surveillance systems spot intruders or find people. Industrial robots pick and place items. Sports analytics track players and the ball. It opens up countless possibilities. Painting by pixels, the art of image segmentation. Image segmentation classifies every pixel in an image. Unlike object detection, it identifies exact pixel boundaries. This means knowing which pixels belong to a car, the road, or the sky. The result is a detailed mask outlining every object. This provides a pixel-level understanding of the scene. There are two main types: semantic and instance segmentation. Semantic segmentation labels all objects of the same class uniformly. Instance segmentation distinguishes between individual instances. Neural networks like UNets or Mask-RCNN excel at these tasks. They learn to recognize objects and their exact boundaries. Applications include medical imaging, autonomous driving, and satellite imagery. Image segmentation is invaluable for detailed image analysis. Beyond reality image enhancement and generation. Neural networks can enhance image quality or create new images. They remove noise, upscale resolution, and colorize photos. GANs generate realistic images and perform style transfer. Healthcare, a new pair of eyes for doctors. Neural networks are revolutionizing medicine, especially in medical image analysis. These tools act as a new pair of eyes for doctors, enhancing accuracy and speed. They assist, not replace, human expertise, improving diagnoses. Medicine generates vast visual data daily. This includes X-rays, Connecticut scans, MRI scans, and more. AI sifts through this data, uncovering vital insights. Early cancer detection is a key application. AI excels in analyzing mammograms and lung CT scans. It identifies subtle disease signs, aiding early treatment. AI also helps in ophthalmology, detecting diabetic retinopathy. Early detection prevents vision loss. AI tools make eye care accessible globally. Neural networks are expanding rapidly in medical imaging. They assist in digital pathology and robotic surgery. The goal is better tools for diagnosis and treatment. Ultimately, AI aims to improve patient health and well-being. The automotive revolution towards self-driving cars. The automotive industry is undergoing a massive transformation with self-driving cars. Neural networks are central to this revolution. They enable cars to see and interpret surroundings with exceptional accuracy. Advanced image processing is indispensable. These networks act as the car's visual cortex. Object detection and tracking are primary functions. Vehicles are equipped with multiple cameras. Neural networks analyze video feeds in real time. They identify vehicles, pedestrians, and cyclists. Traffic lights and road signs are also detected. Lane markings are crucial for navigation. Accurate detection ensures safe driving maneuvers. Many modern vehicles already use ADAS. Features like automatic emergency braking rely on neural networks. Lane keeping assist systems monitor lane markings. Adaptive cruise control adjusts speed automatically. Parking assist systems use visual data. Developing reliable vision systems is challenging. Neural networks must perform under various conditions. This includes weather like rain, fog, and snow. They must cope with different lighting conditions. Human drivers, pedestrians, and animals add complexity. Continuous development and testing are essential. Neural networks have become an invisible yet powerful force shaping our experiences on social media platforms and in the broader entertainment industry. Every day, billions of images and videos are uploaded and shared online. It would be an impossible task for humans to manually review and manage this colossal volume of visual content. This is where neural networks step in, providing automated ways to understand, categorize, and filter these images, significantly influencing what we see and how we interact with digital media. Their ability to process visual information at scale is fundamental to the functioning of many popular online services we use regularly. One crucial application of neural networks in social media is content moderation. Platforms use these AI systems to automatically scan uploaded images and videos to detect and flag inappropriate or harmful content. This can include images depicting violence, hate speech, nudity, or other material that violates the platform's community standards and policies. By identifying such content quickly, platforms can take action, such as removing the content or warning users, helping to create a safer and more positive online environment for everyone. This automated first line of defense is essential for managing the sheer scale of user-generated content and protecting users from exposure to undesirable material. Beyond safety, neural networks also play a key role in personalizing our social media experience and increasing user engagement. Many platforms use them to power features like automatic photo tagging, where the system recognizes faces in your photos and suggests friends you might want to tag. They are also used to organize your photos into albums based on their content, such as grouping all your beach vacation pictures or photos of your pets. Furthermore, the fun and creative image filters and augmented reality effects that can transform your appearance or add animated objects to your photos and videos are driven by sophisticated neural networks that can detect facial features and overlay graphics seamlessly in real time. The influence of neural networks extends into the wider entertainment world as well, particularly in image and video generation. These AI tools are increasingly used to create stunning visual effects in movies and television shows, sometimes generating entire scenes or fantastical creatures. In the gaming industry, neural networks can assist in creating realistic character models or generating diverse game environments. We are also seeing the rise of AI art generators that can produce unique and often breathtaking images based on textual descriptions provided by a user. This demonstrates a fascinating shift where neural networks are not just analyzing existing visual content, but are becoming tools for artistic expression and content creation itself. The world of retail and e-commerce is inherently visual. Images play a crucial role in online shopping. Neural networks enhance this experience, making it easier to find and purchase items. Visual search allows customers to upload images instead of using keywords. AI analyzes the image to find visually similar products. This is useful for discovering items in fashion, home decor, and art. Neural networks also provide personalized recommendations. They analyze your visual preferences to suggest appealing products. This increases customer engagement and sales. Neural networks also help retailers manage product catalogs. They automate tagging and descriptions, saving time and ensuring consistency. In an era where safety and security are paramount, neural networks enhance surveillance systems significantly. Cameras are ubiquitous, generating overwhelming video footage. Neural networks analyze this data automatically, detecting threats and alerting security personnel. Facial recognition technology, though controversial, is a key application. These systems identify unique facial features with high accuracy. Used in security contexts and smartphones, facial recognition provides a secure alternative to passwords. Neural networks also detect anomalies and analyze behavior in surveillance footage. They recognize normal activity patterns and flag unusual events. Ethical considerations, such as privacy and bias, are crucial in deploying these technologies. Responsible development with strong safeguards is essential. The bright side advantages of neural networks in image processing. Neural networks offer remarkable accuracy, often exceeding human capabilities. They learn intricate patterns directly from image data, leading to superior results. Unlike traditional methods, neural networks discover optimal features automatically. Their adaptability allows continuous improvement with more data. Neural networks introduce significant automation and efficiency. They analyze vast quantities of images faster than humans. This automation improves productivity in many industries. Neural networks handle real-world image variability well. They perform robustly even with imperfect images. This makes them practical for real-world applications. Their benefits drive widespread adoption. The hurdles: computational demands and data needs. Neural networks require substantial computational resources, especially for training. Powerful hardware like GPUs or TPUs is essential. Access to such hardware can be expensive. Vast amounts of high-quality labeled training data are needed. Labeling data is time-consuming and costly. The black box nature of neural networks presents challenges. Understanding their decisions is difficult. This lack of interpretability is a concern in critical applications. Developing effective neural network solutions requires expertise. The process involves many rounds of experimentation. Finding skilled talent adds complexity. Navigating the nuances: accuracy, bias, and robustness. Neural networks' performance depends on their training data. They may struggle with out-of-distribution data. Bias in training data can lead to unfair outcomes. Adversarial attacks can fool networks into incorrect predictions. Robustness and fairness are critical for reliability. Researchers are developing solutions for these challenges. Explainable AI aims to make neural networks more transparent. Fairness-aware algorithms reduce biases. These efforts build more trustworthy AI systems. Weighing the benefits and challenges, neural networks' impact is transformative. They unlock capabilities previously unimaginable. From medical diagnostics to self-driving cars, their contributions are undeniable. Ethical considerations like data privacy and bias are crucial. Responsible innovation ensures these tools benefit humanity. Pre-trained models and AutoML platforms lower barriers to entry. Continuous advancements make neural networks more accessible. Despite challenges, the trajectory is positive. Neural networks provide a promising path forward. Their integration will deepen, changing how we interact with visual information. Neural networks are reshaping image processing. They enable computers to interpret visual information with sophistication. This represents a significant leap forward. Neural networks learn from vast visual data, unlocking new possibilities. They give machines artificial sight, evolving continuously. These systems are inspired by the human brain's architecture. They learn through training, refining their abilities. Neural networks excel in image classification, object detection, and segmentation. They enhance image quality and generate realistic visuals. The benefits include accuracy, adaptability, and efficiency. Challenges like computational demands and bias are being addressed. Responsible use ensures their positive contribution to society. The field of neural networks for image processing is not static. It is a dynamic and rapidly evolving landscape. Looking towards the horizon, several exciting future trends promise to push the boundaries even further. We can anticipate the development of even more powerful and highly efficient network architectures. Researchers are constantly innovating, seeking ways to achieve better performance with fewer computational resources. This could lead to models that are not only more accurate, but also faster to train and easier to deploy, especially on devices with limited processing power like mobile phones or embedded systems. Such advancements will make sophisticated image understanding capabilities more ubiquitous and accessible. Another significant direction is the quest to reduce the heavy reliance on massive, manually labeled datasets. While supervised learning has been dominant, it presents a major bottleneck. Future developments will likely focus more on techniques like self-supervised learning, where networks learn valuable representations from unlabeled images, which are far more abundant. We will also see improvements in few-shot or zero-shot learning. These methods aim to enable networks to recognize new objects or concepts from very few examples, or even from just a textual description, much like humans can. This would dramatically accelerate the development of AI systems for new visual tasks and reduce the costly burden of data annotation significantly. The integration of neural image processing with other artificial intelligence domains is also a key trend. We are already seeing the rise of multimodal AI systems that can understand and reason about information from different sources simultaneously, such as combining visual input with natural language text or audio. Imagine an AI that can watch a video and provide a detailed spoken summary, or generate an image based on a complex verbal request. This convergence of senses will lead to more holistic and human-like AI understanding. This will enable richer interactions and more sophisticated applications, from advanced robotics that can perceive and interact with the world more naturally, to more intuitive information retrieval systems. Furthermore, the development of specialized hardware tailored for neural network computations will continue to be a driving force. We have already seen the impact of GPUs, and now TPUs and other neuromorphic chips are emerging. These custom-designed processors are optimized for the types of calculations common in deep learning, offering significant speedups and energy efficiency improvements. As this specialized hardware becomes more powerful and widespread, it will unlock new possibilities for real-time image processing on edge devices. This means more intelligence can be embedded directly into cameras, cars, and appliances, allowing for faster responses, enhanced privacy, and operation without constant cloud connectivity. The journey of neural networks in image processing is an ongoing narrative, one that is constantly being written by researchers, engineers, and innovators around the globe. We have covered significant ground, but the story is far from its final chapter. Each new discovery, each refined algorithm, and each novel application adds another layer to our understanding and capabilities. The quest to imbue machines with a true visual understanding of our complex world is a grand challenge, and neural networks are currently our most promising protagonists in this endeavor. Their continued evolution promises even more exciting breakthroughs in the years to come, keeping this field at the forefront of technological advancement. As these powerful visual AI technologies become increasingly woven into the fabric of our society, the importance of responsible development and ethical considerations cannot be overstated. We must proactively address potential pitfalls such as algorithmic bias, which can perpetuate or even amplify societal inequalities if not carefully managed. Concerns around data privacy, the transparency of AI decision-making, and the potential for misuse of technologies like facial recognition or deepfakes require thoughtful debate and robust safeguards. Our collective responsibility is to steer the development of visual AI in a direction that is fair, accountable, and ultimately beneficial for all of humanity, ensuring that progress aligns with our shared values. Beyond solving analytical tasks, the future of neural networks and image processing also holds immense potential for unlocking new forms of human creativity and accelerating scientific discovery. AI-powered tools are already enabling artists to generate novel visual styles and explore imaginative concepts previously difficult to realize. In science, sophisticated image analysis can help researchers decipher complex patterns in everything from microscopic images of cells to astronomical data from distant galaxies. This synergy between human ingenuity and machine intelligence can lead to breakthroughs in art, medicine, materials science, and many other fields, opening up new avenues for exploration and expression that we are only beginning to tap into. In concluding this exploration, it is clear that neural networks have irrevocably transformed our relationship with visual information. They have provided us with tools of unprecedented power to interpret, enhance, and even create images, leading to tangible benefits across a vast spectrum of applications. While challenges remain, the pace of innovation is relentless, promising a future where machines will perceive and interact with the visual world in ways that are even more intelligent and intuitive. The unfolding narrative of visual AI is an exciting one, filled with opportunities to build a future where technology enhances human understanding and capability, making our world more knowable, navigable, and perhaps even more beautiful.